In this chapter, we will use this graphic to talk about key dimensions in triangles and vector force calculations.
When it comes to your bicycle wheel and your spokes made with good stainless steel, it's important to mention you must measure spoke tension. It's something you can't do by feel. Throughout this video, off and on, we'll talk about wheel geometry quite a bit, but let's start out with some basics of the geometry of a bicycle wheel.
Here's a generic bicycle wheel. Let's look at it in cross-section. Here's the hub at the center of the wheel. This is an axle, lock nuts on either end. Here's where the gears attach, and these are called flanges. The drive side is on the right and the non-drive side is on the left of the hub, so the hub has a right side flange or a drive side flange and a left or non-drive side flange. This is the rim. These are the spokes that attach to the drive side flange. These are the spokes that attach to the non-drive side flange. This graphic will be the basis of our discussion. This line bisects the wheel through the center of the rim, and that divides the hub into two pieces of equal length. Our rim is a velocity diad with 32 holes, and it has an effective rim diameter of 597 millimeters. Effective rim diameter, usually just expressed as the abbreviation ERD, is a measurement that wheel builders take and is used to calculate spoke length. If you're not building a wheel, it's not necessary that you know anything more than that. The effective rim diameter is usually about 10 or 20 millimeters more than the internal diameter of the rim. Our hub is a Shimano 105 hub with 32 holes. It has a hub flange diameter of 45 millimeters. It has a center to right flange distance of 18.5 millimeters and center to left flange distance of 35.5 millimeters. We have two right triangles. By using a spoke length calculator and figuring a 3-cross lacing pattern, I determine I have drive side spoke lengths of 289.72 millimeters and non-drive side length of 291.29 millimeters. Within these two right triangles, I'm going to study two angles, this one theta and this one phi. The sine of theta is the opposite divided by the hypotenuse, and that would be equal to 18.5 divided by 289.72. So theta is the arc sine of 18.5 divided by 289.72. Theta is the arc sine of 0.064, and theta turns out to be an angle of 3.67 degrees. Similarly, the sine of phi is also equal to the opposite over the hypotenuse, which in this case is 35.5 divided by 291.29. Phi is the arc sine of 35.5 divided by 291.29, which is the arc sine of 0.122, and that comes out to 7.01 degrees. On the drive side of the wheel, we're going to put a force on the spoke equal to the tension on the spoke. And there is the vector representing the tension. And the amount of tension is going to be 130 kilograms of force, which is also 1,275 newtons. So I better introduce you to this term, kilogram of force, a term that wheel builders frequently use. Well, I know that force is equal to mass times acceleration. In the case of a Newton, the definition is a kilogram meter per second squared. But what if I'm talking about gravity? Then my acceleration term is 9.8 meters per second squared, and that is the definition of a kilogram of force. So 1 kilogram of force is approximately equal to 10 newtons. We saw here that my tension expressed as newtons is 1275, which is almost 10 times 130. In fact, it's exactly 9.81 times 130. Now, the tension on the drive side spoke can be resolved into a vertical component and a horizontal component. The vertical component tension is equal to the tension on the drive side spoke times the cosine of theta, and the tension on the horizontal component is equal to the tension on the drive side spoke times the sine of theta. So that becomes the sine of 3.67 degrees times the tension vector, and that is equal to the tension vector times 0.064, and that comes out to 1275 newtons times 0.064, or 81.6 newtons, which is also 8.32 kilograms of force. 8.32 kilograms of force represents the length and tension on that vector. On the non-drive side of the wheel, we're going to put a force on the tension on the spoke on the non-drive side, represented by that vector, and that tension is going to be 68.2 kilograms of force, or 689 newtons. This vector can also be resolved into vertical and horizontal components. The tension on my vertical component is equal to the tension on the non-drive side vector times the cosine of phi, and the tension on the horizontal component is equal to the tension on the non-drive side vector times the sine of phi, which becomes the tension times the sine of 7.01 degrees, which is the tension times 0.122, and that works out to 689 newtons times 0.122, which is 81.6 newtons, or 8.32 kilograms of force. An important observation is that both of these two vectors are the same. They both represent a tension on the spokes of 8.32 kilograms of force. When I multiply the length of that long vector by the sine of that small angle to get that vector there, I get the same result on the other side when I multiply the length of that shorter vector by the sine of a larger angle. I could also show these two vectors up here, and these two vectors have to be of equal length for the rim to be centered over the hub. And the lateral stability of a wheel is related to the length of those two vectors. This picture here represents a more laterally stable wheel than this picture where the vectors are shorter. Let me step back and answer a question that may have occurred to you. When you build a wheel, you determine the lacing pattern, and then you determine what tension you want to put on the drive side spokes. And in this case here, I have put a nice healthy tension of 1275 newtons on the drive side spokes. The question is, how did I know what the tension would be on the non-drive side? How did I know at the outset that I would need 689 newtons? In fact, I don't. The drive side tension you can think of as an independent variable, and the non-drive side tension you can think of as a dependent variable. We know that the horizontal tension on the non-drive side spokes is going to have to rise to the level that we set for them on the drive side. And I know these dimensions and angles that I determined a minute ago. These are independent of the tension. These are just based on the basic geometry of the wheel. For some reason, if we wanted to calculate from the beginning what our tension is going to end up being on the non-drive side, we would start with the drive side information that we have and say that those two numbers representing tension on the drive side, horizontal vector, will have to be the same on the non-drive side, and then we can work backwards in order to determine the non-drive side spoke tension that will give us that result. I like to express it this way: when the wheel is completed, the tension on the drive side is set to what you want it to be, and the wheel is dished so that the rim is centered over the center of the hub. The tension on the non-drive side is what it is. You have no control over it. There are some things that will improve lateral stability. One is a rim with a smaller effective rim diameter, a hub with greater flange diameters, a hub with a greater center to right dimension and center to left dimension. Fewer crossings means shorter spokes, and using optimal spoke tension helps also. It would be more accurate to replace optimal spoke tension with adequate spoke tension, as you will see later. Unless the tension is very, very low, adding more tension does not really have the effect on lateral stability that you think it might. I suppose it would be really great if I could take all of these variables and plug them into some formula that would spit out the correct combination. But in reality, we have the rider's weight to think about, the type of bicycle, the intended type of riding, and all kinds of other things. There's a balancing act that you have to take into account, pros and cons of different options, and use your judgment to come up with the best overall combination.